Sir, I can.
You see, I had sent a message again. Are you able to see the message?
Yes, sir.
Yes, you have to write there only.
Message. No, sir. Invisible. Sir.
Message invisible. BN
Short.
Mishra,
Short. हाँ
are
सर
you
ये
there?
मिस यस
BN
सर
Mishra, are you
हाँ
there?
सर yes sir have done them sir का roll number only
Roll number, roll number. You write your roll number. Write your roll number and full name. You see, Chinmay, it is coming.
yes
Okay,
sir yes sir
okay, okay. What's your full name, BN Mishra? What's your name? Okay, Baradanandan Mishra. Okay, someone else is there also. Yes, yes, yes. Thank you, Chinmay.
thank you sir
Okay, all are requested to please write your name and roll number in the chat box. So, can I start the class?
yes sir
Okay. So, here we have to discuss MCSE-11, which you all know that we have to discuss about parallel computing. And if you look into parallel computing and if you want to understand the subject also, there are different parts of units you have, and you most probably you had gone through the part of your syllabus also. So, as per the requirement, if you are looking into what we have to understand and what we have to uh, look into, like if somebody wants to understand that, I can possibly say that here we can go for different part of your jobs to do, where you could understand what different type of particular processors, what different type of architectures we are having, and so what different architectural differences you can go for. Those things we can find it here. Are you able to see the PPT now? I'm scrolling. Hello.
sir yes sir yes sir
Yes. Okay. uh, Here uh, we are going to start with that subject, and if you remember, in your first unit we have three different things to discuss. First, the basics of parallel computing. Then second one will discuss about different architectural classifications, that's like Finch classification, Handler classification, and then go for Fink's classification, then computing structures, and so on. Then the third one is supposed to be different networking structures, that what kind of network architectures we have, and finally we go for architectural differences. So these are four different things we have in the first unit of book, and that we have to start today with respect to the part of your concepts. So here comes the parallel computing overviews. Now, if you really wants to go for different requirements, we can say why this motivation comes to us, that we have to think of that parallel computing is required. What is the necessity behind it? If you ask for, we can find many answers in many different books. But remember that at this particular point of time, if you look into the modern architecture era, here I could say that modern architecture is consist of many different versatile processors depending on different type of requirements, and there may be many changes also appears in different possible tasks we have. and this could be one of the way we can go for, and that could be the part of your process we can go from time to time. So you can say that here, if you go for different processors, you can think of also different. Please mute from your end. Okay. So here we can think of that what better way the processor can be taken care of. Then next is that if processor is there, how we can able to go for better computation on the processor. Then think of, if better computation is there, we have to provide better data to the system. So here it is not a matter of the processor. It is not a matter of the part of your processor which we are going to execute with. It is a matter of different part of requirements which we can think of to add from time to time, and we can say this particular part of things we have to go for one after another, so that we can add them as new features to the system, so that whenever we want to manipulate, we want to enhance the computing, we want to moderate the computing power, that can be supported. Very basic example, if you remember, from your operating system, we say that a computer is not having any memory device whenever it is started. But whenever we think of simultaneous peripheral operation online, or we can say spooling, then at that particular point of time, we are adding the hard drive to a system or disk to the system, and we are thinking the system can able to do executions more faster. And here comes the introduction of the DMA to the system, and the system would do better when it is segregated from the part of your IO computations. So we have CPU computations, we have IO computations. So when you are saying CPU will do only CPU computations, in case of using the spooling, the CPU will be perform better in comparison to doing both the things when a IO controller is not available. So that's why we can say evolution of supercomputing definitely not depends on the architectural changes, but also it depends on what kind of processor, what kind of particular procedure, what kind of particular architectural classifications, and what kind of amount of data you are using at one point of time. So this different kind of possible data, if you are going for, then only the possibility to go for programming parallel computers can happen. Now if you remember that how a data is retrieved, a very small example you can think of, a data can be retrieved in very different way. So you are writing what? A. You sometimes you supposed to write what? Sometimes you supposed to write, let's take here A equal to 5. So what does it mean? This is a scalar data. And if you are asking for a scalar data here, then we can go for only one particular variable. This will be assigned with a register, and we can able to store what? Only one data. And this may not be the part of your way where we want to achieve supercomputing. This can be much more better. So instead of going for this, we can think of that, yes, we can do this. So this could be go for a vector, and I can store here. Let's take 1, 2, 3, 5, and here more number of data I can store. And here what I can do, if I'm asking for a of 2 at this particular point, I can bring the whole a. What is the harm in that? So it might be a case for this instance of time. Let's take a t1 time. I am using a of 2, and whenever we go for T2, which is very different from the T1, non-overlapping time slab, if I am going for, and here I got the whole A instead of, so what you did, instead of bringing this only index, you brought the full array. So if you brought this, now you see your time 2 asking for A of 4. Now, if you brought that before, now it will be a hit, it will not be a miss. So we have to think of how better way we can able to retrieve the data also. So if you go for a better computing device, it will not work only. You have to give the proper support from the data also, so that we can say that parallel computing can be possible, or the supercomputing can be possible with adequate amount of data supply also. So this is what the behind background story before going for the part of your faster computers. So we can say that we want to save time. So saving time is one of the best way of structures. And then if you go for solving this particular problems, the different intensify problems we have. So sometimes we can go for infeasible problems to make it feasible. Sometimes we go for the design issues to solve. Sometimes we go for larger problems to break down into smaller problems and we solve. We can also think of that, how to reduce the design time. We can think of how to reduce the part of your setup time, that we can able to work on. And finally comes to the computation. So in the market normally this computation is going on, and we believe the computation, if not there, then definitely computer do not have these variety number of differences of classifications. If you look into from the architectural view, if you look into from the data perspective view, if you look into from the pipeline perspective view, from the processor speed perspective view, so different perspective criterias we have, based on which your computer systems has been developed, and they can possibly go for different possible ways to work over there. Now comes to the part of your basic concepts, based on which it starts with. We can say that parallel computing. So using parallel computers to solve single particular problems to make it faster. So we can say here, I can possibly go for a client server model. So parallelly many remotes are working, and it may be a case the server will work with the part of your help of your remote machines. Now coming to the parallel computer. So parallel computer is a part of your multiprocessor system supporting parallel programming. So this is your message passing, or we can say MPI. So open MPI is a platform, and here everybody can able to communicate from one to other, so that we can able to get the job done as quick as possible. And last one is coming to the part of your parallel programming. So programming in terms of that, we support the concurrency. But there is a big difference here. I would like to tell you, if somebody wants to understand that, what the difference, I would like to go for the understanding would say that we can find out the part of your different possible ways of going into uh, the programming concurrency. That means concurrency says there are two different programs are running parallelly, and here we have to understand that if concurrency allow them to execute parallelly, they must have a non-overlapping time span. That means to say, here we can say concurrency may allow every process to run at the same time. So here comes the part of your timeline. We can say A job, B job, C job may starts at the same time, but I cannot ensure that whether this execution can be possible till the end of the requirement or not. So we can able to go for the requirement here, and we can able to find it out with respect to the parallel programming. So they can start their executions parallelly, but due to their execution demands, let's take, we can say A program is depend on B program depend on C, and then C program is depend on D, and so on. If this functional dependency is there, we can possibly say, so A has to be executed first, then only B can be. So at this particular programming concept, I have to believe that that we will start the program here with begin and end paradigm. So can you tell me that whenever I am enclosing some program in between begin and end, what is going to happen? What is the meaning of this begin and end? If I write A B C, what will happen? Anybody? Do you have any idea? If I do this, what is going to happen? These programs will execute in what manner? Any idea? Are you all there? Please respond.
Yes, sir.
Yes. Please tell me if I'm going to execute A, B, C in the paradigm of begin and end. So what is going to happen? These programs will execute parallelly. These programs will execute concurrently. These programs will execute one after another. How does they react for the execution? Any idea?
One after another, sir.
Begin. Okay. Very
Begin
good. Yes. Begin and end will say
and
we can go for a serial execution.
serial.
A serial execution, and this understanding tells if I will use a begin and end paradigm here, we can able to do the executions and, in a dependence manner. If dependency is there, like what I told, if A is depend on B, B is depend on C, and C is depend on D, so here A has to execute first, then only B can be, and this begin and end will work, and we can able to say that processes will execute one after another. but
Yes.
let's take but let's take somebody don't wants this. Somebody wants that I would like to go for a part of your execution where A is not depending on B. I want that A and B should be executed parallelly. So what should I do? But I have a dependency from B to C. So B is depending, B is somehow executed first, then only C can be. So C is having a dependency on B. So if it is correct, but there is no dependency between A and B, so how can I change the paradigm here to attend the parallel execution? So I can make some slight changes. So I can go for begin. So I will definitely allow it for the end, and at this particular point of time here I can add something different. So that's supposed to called as co begin. So this co begin in some books also written as the part of your co start. In some books it is written as para begin. Some books it is written as the part of your para begin and para end. So this says that we want a parallel execution. So now I can keep it here: A, B, O, end. Then I can have what? C. So here comes the situation that says that A will be executed, B will be executed, then C will be executed. But now you see A and B will be executed at the same time, but C will be executed after the execution of A and B. So this is supposed to be called as that how your programs will execute depending on the requirement of paradigms. Whether you will go for parallel execution, whether you go for a sequential execution. But can you tell me what exactly a concurrent execution is? Any idea regarding the concurrent execution? What exactly the concurrent execution works for? Any idea? So if you try to understand a concurrent execution, the concurrent paradigm is slightly different. Slightly different. Why I'm saying, it says that if A is going to start at T time or T1 time, it will go for the execution. B will start only after some executions of B. So A is temporarily suspended. It starts at T. Then here we can say B is not B is started, A is not completed. So I can possibly say C is also started at T3, but A is not completed, B is also not completed. That's why we can say this is a concurrent execution. A is running, B is running, C is running. For example, what you are also trying to prepare a document, you are also filling a data into the Excel sheet. So you are migrating sometimes from MS-DOS to MS Excel, MS-DOS to MS Excel. That does not mean that that you are parallelly working. You are working with one, then you are switching to next. So you are continuing with two different programs. So that's supposed to be called as a concurrency. But remember, in this case, there is a negligible gap, or there is a zero gap whenever you are switching from one task to the other task. So this could be the part of your non-overlapping time span execution. So A to B, B to C, and so on. So in this case, if you ask whether I got a parallel executions or not, I would like to say no. Every concurrency or every concurrent execution cannot be possibly go for the part of a parallel execution. So why so? Because if you can say only that the language that we support the concurrency only to find the co-begin and co-end, that's all. But in concurrency definition, we have this non-overlapping time spans. So if I go for non-overlapping timestamps, clearly it spells out that it is not a part of your parallelism. So if you really wants to achieve parallelism, what you can do, you can add that non-overlapping time span to overlapping time spans. This is your overlapping, sorry, A, B, and C. Overlapping time span. Every process will start at T time. So this is what we have at this particular point of time to work out with, so that we can able to understand what exactly a parallel programming is. So remember, every parallel programming is a concurrency. That's why it is written. But every concurrency is not a parallel programming. So we have to remember that what we are working with and what programming language supports this kind of things explicitly. Because retrieving, just before to this I told you, retrieving a data, whether from a array, retrieving a data from a scalar variable is completely different. Because if you are bringing one data, you are bringing one index, that's completely okay. But if you are bringing the complete array, now challenge will come before the processor. What is the challenge? The challenge is supposed to, can I have space to store that? That makes a point of changes to appear. And Intel company works very nicely on these kind of challenges in the innovation of your computers. Not only computers, to the processors even. Now goes to the part of your other end, where we can go for further requirements. So further requirements is that MPI I told you already. So this main parallel language we are using in processing of text. So OpenMPI takes care of this particular part of your possible requirements. So OpenMPI is the parallel paradigm which we are using for the part of your parallel programming. Now comes to the part of your classical science, from which this parallel programming came into picture. So everything you know depends on the nature. Without the nature we cannot start. Let us start from the nature, and we observe many different case studies, and many different case studies will say what we have lot of works to do parallelly, and they are all theoreticals. But if you are thinking of the theory, then a physical experiment must be available. But we have to go for our thinking beyond our comfortable zone. So if you can think of, then only I can possibly say the physical experiments can able to get back to the observation. So think is that how better way your theory and experimental things can come to the observation, and we can meet each other, so that the parallelism can be achieved. And this particular science further modified for our requirements. So what we do, we go for this particular requirement to identify in different possible tasks where I could add so theories of numerical simulations. So we can go for, actually I cannot enter into a part of your chemistry lab where I can do some titrations and tell you some figures, because it is a completely computation field, and we are going to discuss about parallel computing, so that I would like to go for some of numerical simulations. And these numerical simulations can go for the scientific issues, so that we can able to reach to the observations what we observe. Let us look into the observations, what observations we have, and those observations can be followed further for the implementations or not. So that's very very important. Now if you look into this particular part of your computations, starting from 1989, really we are working, whether it is a platform of quantum chemistry, whether it is a platform of statistical mechanics, and any relative physics. So you can think of getting the theory of Newton's law, getting the theory of different law, that is fluid of mechanics. We can go for buoyancy law. We can go for many different laws, depending on which every challenges of our day-to-day life come to one spatial solution. And that can be also possible in case of this numerical statistical calculations. So if you go for any field of science, they really working on different possible laws, and those laws will work very nicely to give you a customer friendly or a user friendly solution. And we are also expecting the same in this same scenario. And we can also say that this could be the part of your best option to find out the solution. So one example I had taken, so that we can able to go for a weather prediction schemes. So you can think of the weather prediction, how we can able to go for. So we all remember, I do not know whether you remember or not, because during 99 we also have a weather prediction for the cyclone. And in 2018 also we have a weather prediction for the cyclone. And if you experience 99 and the prediction of 2018, there is a huge difference. There is a clarity of data produced by the meteorological department, and that clarity goes for the scenarios to scenario we can think of. And if you go for the part of your last hit cyclone to the Sundarban, the meticulous calculation goes on the part of your altitudes and attitudes meet to the point of particular land. So that makes a very very different, that how we are predicting, and how better way the things are coming into the proper clarification, that what makes it better and what gives you better, and what is the thing behind it. So definitely the well prediction rules definitely supports to that. Now this definitely supports to our evolution of supercomputing. And we definitely believe the supercomputers, what we are coming to here, that must be powerful with respect to the current build, with respect to the traditional systems. So they may be dependent on the time, they must be dependent on the operator, who are the hands they are in. They must be depending on the computation speed, that you are talking about horsepower. Then we also think of that in which field they are supposed to give the correct accurate answer with speed, with accurate calculations. And then we can possibly say that we can go for the designing purposes with respect to nuclear weapons. So the intelligence gathering, then code breakings, these are some of particular design perspectives which the supercomputing adding on, and creating the dependency of the user time and again, time and again, time and again, we can able to believe on. And these evolutions not only started from the parallel computers, but also going for super parallel computers, but supposed to go for super pipeline computers, then very large instruction word computers, then go for the part of your Thomas law, then we can go for the part of your systolic arrays, then we go for scoreboards, then we can have quorum computers, and so on. So it's not a small list, it's a huge list. If you look into that, evolution of supercomputer came into picture, and they had given their foot marks in different field of working, and people user believe on that this evolution is the most beautiful evolution in the structure of the use, where we can take many help, so that the human perspective systems and their respective requirements get as much as possible help when as they require. So this is what we have. Then comes to the day-to-day life of supercomputers. So general purpose we have, yes, solving individual problems, yes, that we can, but the cost is really high. That is comes more than 10 millions. So a general idea we can say, originally we have to think of that how exclusive, and how exclusive the situation is, and how exclusive you are going to make use of. So commercialization have some problems depending on the field you are working on. So this commercial supercomputing systems we have, but this possibly there depending on the cost you are putting. So that's why very rare systems where it is really required, we can go for a choice. Then you can think of that from where we started. We started with what? Flip-flops, or we can say we started with transistors, or we can think of back, we started with vacuum tubes. So vacuum tubes, transistors, then go for resistors, then transistor and resistors, then we go for the integrated circuits, then go for large integrated circuits, then go for the part of your very large integrated circuits, and so on, increasing. So what we are increasing? We are definitely increasing the part of the number of the devices inside a processor. And what we demand? We demand how faster it can be. So we can go for how faster we have this particular flops or flip-flops too. So coming from a number of 350 to 1 trillion is really a big gap we are going for. And if you go for the CPUs, it will be much faster in comparison to with this we can go for so greater systems with concurrency, multiple functional unit, concurrent instruction executions. Then we can go for out order scapulative means out order executions. So we can possibly say, I would like to say what exactly is the part of your in order and out order. Let's take A equal to B plus C. Now you see, let's take D equal to A plus E. Please try to understand what I am trying to say. If I'll go for A equal to B plus C, now you can go for, let's take Z equal to B plus Q. Now anybody can tell me what is the difference between these two different set of examples? Anybody can guess what exactly I am trying to say here? What is the difference between in order and out order execution? Anybody have any idea, or anything you understand from the example? Please. Okay, so in the first one you can see there is a dependency from the first instruction to the second instruction, and we understand that if I have this dependency, that can be very nicely understood, that if I am not executing the first one, the second one cannot be executed. So that's why this instruction sequence cannot be changed. This is going for in order executions. So what I'm going for, I'm going for the part of your, let's take we have in order executions, and this part of your in order executions definitely go for the second example. So second example can possibly go for the out order. So here you can see this instruction and this instruction do not have any dependency. So if I execute in this way, okay, if you are executing Z first and then go for evaluating A also, there is no harm. So that's why this is supposed to be a part of your what? So this can be the part of your speculative instruction executions. Any way you go for the execution, that is only depends on whether you have that functional unit or not. If your functional unit is available, you can very nicely go for the executions here. So we can go for faster executions, processor having 1 million times faster, and we can go for that to achieve much more. And parallel computers definitely say that multiple processors can support this, and we can get the support from the multiple computers where the program can be executed much more faster. So coming to the final, what I really wants to say, you go for any science, there must be a law working behind, and here the law comes. Gordon Moore, 1965, given many observations, as I told, the nature gives many observations. Apple come down from the apple tree from the top of the level to the down towards earth. So Newton find out a law. So this is not this looks to be very silly, but finding the gravitation law from out of it, and we can say not that much easy. Now if you go for the part of your requirement with respect to the different possible task, with respect to number of chips, with respect to the exponential range of the cost, with respect to the capacity of storage, with respect to the area of the processor. So we came down from 45 nanometer structure to 4.5 nanometer structure. Moore's state many things. So processor may double the speed in every 18 months. That means you have to provide much more data in every 18 months. And if you provide much more data, you have to store much more data. And where you can store, until and unless you will not increase the storage device. So Moore's law is a law, the backbone of we can say Intel success. We can say that works everywhere at every point of time we are looking into. And if you are thinking that this will work, yes, this will work not only for the processor but also for the IOs. That means if you are storing much more number of data, how the particular data will reach to the processor, until and unless you have a very nice IO controller. So we have to give the proper IO controller, and Intel is the first company who had given front side bus, FSB. So this innovation done during the time of millenniums or 2000, we can say, and that makes the powerful machine in Intel, where your Motorola, Z80 and others, AMD Athlon, not able to compete with. So this FSB system gives a better activity to retrieve data on your part of your IO devices, so that we can able to understand that we are not only working on the processors to double the number of transistors, register, or going from large integrated circuit to very large integrated circuits and so on. We can possibly say in this possible case, I can able to go for the further things. So at this particular point, and we can possibly go for the reduction in case of your work time, reduction in case of your part of your consumption of the CPU time, and we can able to get better throughput out of it. So Moore's law works very nicely for the success of the Intel designs, and it works till now today even. So this is your Moore's law. You can see many computers, mainframe computers, and now we reach to the part of your supercomputers, and finally comes to the part of your different part of your success stories from time to time we have. So many computers are to be used, mainframes also, supercomputers also, and the final call log for the micros. So finally comes to the computer size. We can have some of names, and then go for the part of your different parallel models. So different parallel models to available with n cubes, Intel supercomputers systems, and we can also thinking of machines to cooperate to start with CMC 265, 345, 535, and single bit processors. So these are different innovations time to time occur. Then this is very nice thing we suggest, copycat strategy. So copycat strategy will always go for 1% speed up of computer. That means every time this has to be enhanced. So cost has to be increased by 0.1, and parallel computers with 1000 microprocessor has to be potentially added. And remember that we need to go for with 10 times more speed of the computers, and that's supposed to be the part of your point where with the same cost we have to work. So it's not like that within a night everything will change. We will go on adding things, and that will make a proper difference over here. So if you go for the processor level, it is very less. But whenever we are coming for the computer level, it will be much more high. And if you increase the cost, then user cannot support it. So we have to do everything in the same cost. That's why that is a challenge also. Many particular time, that is also a challenge. How come we can do that within the same time? Then coming for everybody, we can possibly go for the CPUs. So if you ask for everybody what they say, you just give me this megahertz processor. So why did not everybody buy one? So we can say they depends on the part of your CPU. So computation changes. So we can go for adequate changes in IOs. We can go for adequate changes in operating systems. We can go for adequate changes in the programming environment, and that makes it different choices from person to person we can do with. So this is what the choice brings, the differences in your system, and that also helps to go for better innovations in the field of supercomputers. Then coming to the mid of 90s, we can also have IBM's HP, Silicon Graphics, and Sun Microsystems, who had given a very nice footprint to give you a better supercomputing system. So IBM mainframe systems are most good, and Param was one of the set designed from the IBM only. So these are the stakeholders starting from 90s onwards. Then going for the commercial parallel systems, we can go for the cost. We can also think about the software developments. We can also think of the cells, so that we can able to sell it or not. So do it yourself in an alternative manner. We can think of whether we are increasing the speed or we are decreasing the speed, so that we can able to analyze whether we are on the right track or not. Then coming to the subject point, that how we could able to go for. So this I already told you in the beginning. What is concurrent event or processes which seems to be occur or progress at the same time. So we seems to be at the same time, but really they are not. And if you go for the parallel events or processes which occurs or progress at the same time, so you can see what's the difference of words event of processes which seems to be occur or progress, seems to be, but here they occurs the progress at the same time. So the concurrency, we can think of that I am working parallelly in MS DOS and Microsoft Excel. So MS DOS and Microsoft, but that is not really happens. We are working at one and then we can switch over to next. So that means to say we really not working on that. So this is what the part of your difference in between the concurrency and parallelism. Now, whenever I'm coming for the parallel programming, in case of parallel programming, we think that the computer programming technique that provides for the execution of operation concurrently, we can think of that a single parallel computer or across the number of systems in this system we could work with. And further we can think of whether we can go for the distributed computing software. So this is what the concept to start with, and we can go further in this case to start with the part of your Fling's taxonomy. So this can be the part of your classification scheme to start with your book sections, and we can go for the part of your second unit to start over the requirement. And here this could be a part of your classification where we can exhibit different particular requirements like instruction stream, data stream, and so on. And this sequence of instruction stream and data stream can be operated out with respect to the part of your needs and requirements. So whenever you say that we will go for more number of data, whenever you say a single number of data, whenever you say single amount of instruction, when you say single amount of data set. So depending on that, it will vary from time to time. So let's see what we have. We have basically 4 combinations. Most probably you know these things in the architecture part. So one can comes as a single instruction, single data, then go for single instruction, multiple data, then we have multiple instruction, single data, and finally we go for multiple instruction, multiple data. So this kind of possible task we can go for. So single instruction, single data, we have a single CPU system and I don't have to go for further. So this is completely a unique processor, and concurrent processing is supposed to be a challenge over here because we have to go for the execution 1:1. So concurrent processing is allowed, but getting a challenge because of the instruction fetching. How many number of instruction you can fetch at one point. So pipeline executions of instructions can be possible through this. That can be said, and functional parallel executions are allowed, and we can able to go for independent instructions or task to execute one after another. So this could be one of the best example of your personal PC we can work for. And how do that look like? This can be look like here. That's we have a single particular part of your CPU, and this single CPU must take the input from the instruction stream, then go for connectivity to the memory, and this memory will give the data to the instruction stream, because your instruction is also a data. And in this memory, what we have, we must have our instruction. We must have our instruction as well as we also have our data. Now both can possibly go to on the part of your instruction stream and data stream, and we can possibly work with the execution. So here comes the part of your execution. Processing will be done here. So instruction stream and data stream. So single CPU system we can consider for. Now if you go for single instruction and multiple data, this is also one of the case I can go for one particular case of evaluation, and this case of evaluation will help you to understand many different things. So here I have single instruction, and this single instruction will take me to the multiple data stream, and this multiple stream can possibly work with multiple number of ALU devices. So I can possibly go for each processor, and part of your executions called as processing elements, and every way it is a ALU, we can work with multiple number of processing element. But processing element do not store the copy of the program, and here the program has to be with the control unit, and that will be controlled from the point of the control unit form, and individual processor can be taken into the consideration for their executions. So SIMD can go for all active processors to work with, and they can possibly go for the execution from time to time. Let's see who joined. Disconnect. Okay. So who joined? Okay. So here we can go for the part of your SIMD processors to work with. So we can go for single instruction, multiple number of data, and then we can continue with multiple requirements. So this must be the part of your array processor we can call for. How, if somebody say how does it look like, we can possibly say, and this can possibly go for looking like something here, supposed to be like how we can say, let's see, we have a single control unit. Uh, so this will have a single control unit, and we have different processing elements. We can go for different processing elements. And then 1, 2, 3, and so on. So this will be connected with this control unit. And remember that these are individual processing element, and this processing elements, now if you see, they are connected to a shared memory, and this shared memory must be used for a common storage. So your program will be here, as I told. This program will be over here, and this program must be given to the control unit, and control unit takes the decision to whom he has to pass out the program. And if you ask for the control unit keeps a control memory, a small space. So control memory is available here. This control memory keeps some data so that it can able to help your processing elements at the time of executing the particular particular part of your task, one after another. So this is what the part of your SIMD works with. Now comes to next, we can go for the part of your SIMD. Then we can go for multiple instruction and single data. Multiple instruction single data is a theoretical approach, because if you say multiple instruction and single data stream at this particular time, we cannot go better. Why? Because this could be a category of requirement with respect to need, but we cannot say this can be a approach which can be practically possible, because this will increase the dependency. Multiple instruction depends on the same data, so it will only create dependency. So achieving parallel execution with respect to the MISD is theoretically possible but practically not possible. So that's why this implementation do not have a architectural diagram. Then go for the part of your MIMD. So we can say this possible task will help you to achieve maximum parallelism. So multiple instruction, multiple data at one particular point of time we can work with, and the processor and their synchronizations must be done from time to time, and we can possibly remember that what type of different necessities we have. And here we can use this as a multiprocessor, and we can able to communicate through a shared memory, and whenever we write to a specific memory model. So this will be considered as the most powerful machine with respect to our need. And this can have a change in the system. We can possibly say I have single control unit, I have a processing device also. So single control unit we have, then go for a processing element, just modification in your array processor. So array processor now becomes multiprocessor. So you are giving one control unit, that's why it will take a lot of time to take the decision. Now you see I have single memory modules for each one. So this memory module has been created for exclusive write operation. Exclusive write operation. But if they want, they can read everywhere. So we can say here read everywhere. So this kind of arrangement has been done for a part of your multi-programming with respect to multiple instructions with multiple data stream, and we can possibly achieve a better result in case of MIMD. Question can ask that what is Flint's classification and how it works, what are the different divisions, you can answer. Then we can go for the common paradigms for the part of your requirement, where we can able to divide our multiprocessor into different tasks. One will be called as uniform memory access, other will be called as non-uniform memory access. When we try to understand what is exactly a uniform memory access, I could say I am working on a client server model. That means I have a processor, I have a processor, I have a processor. Let's take P1, P2, P3. It is connected with a cache. Let's take connected with a cache. Let's take connected with a cache. Now, if this class is going to be further connected to a IO device, and this IO device is further connected to a common main memory. So we have a common main memory here. We have a common main memory here, and this common main memory is supposed to take out all the data for processor 1, processor 2, processor 3, and so on. So in this case, the data whenever we are accessing from this main memory, it is always uniform. That's why this system is called as uniform memory access. And this system of working is supposed to called as tightly coupled system, centralized system. This is supposed to be called as a multiprocessor with UMA access and so on. So this is what we can possibly ask for a different type of UMA access with your multiprocessor schemes. Now if you go for part of your remaining, we can also say I have a non-uniform memory access. Let's see Now you see here we have individual main memory, and all main memories are connected to a network. All main memories are connected to a network. So this is supposed to be called as loosely coupled system. And whatever be the data we are retrieving based on our own main memory. That's why it is called as non-uniform memory access. What this called as? This is supposed to be called as non-uniform memory access. So here I can understand that at this particular point of time, if I go for the part of your different processes to work, we can definitely work out with the multiprocessor systems with respect to non-uniform memory access or the part of your uniform memory access. So this is what for okay. So we will stop our discussion here. Anybody need to ask any question? Yes. Anybody need to ask any question here? Anyone need to ask any question? All of you, please write your roll numbers. I think someone has not written. Chinmay, BN Misra, here. Smitanjali, are you there?
Yes, sir.
Please write your roll number in the chat board.
Okay, sir.
Yes. Yes. Thank you. Thank you, all of you.
Thank you.
We will discuss the next part tomorrow. Thank you.
Okay, sir.
Thank you all.